the definition of an FOL sentence is more complicated than the definition of a TFL sentence. In particular, we construct FOL sentences from FOL formulas. So we first need to talk about what FOL formulas are. Our first new concept here is the concept of a term. A term is any name or variable. Atomic formulas are either sentence letters or constructed from terms and predicates. So in particular, the official definition of an atomic formula goes like this. Any sentence letter is an atomic formula, and if R is an n-place predicate and T1 to Tn are terms, then the result of applying R to this sequence of terms is an atomic formula. So say if you have a two-place predicate and a sequence of two terms, then the result of applying this two-place predicate to your two terms is an atomic formula. Then third, if T1 and T2 are terms, then T1 equals T2 is an atomic formula. And finally, nothing else is an atomic formula. So that's our definition of an atomic formula. Here are a couple of examples to illustrate what's meant. Fa, Gb, H, C7, those are all atomic formulas. So what we have here is simply a one-place predicate, F, G, or H, that is applied to a name, A, B, or C7. Now similarly, Fx, Gy, or H, X subscript 19, all of these also are atomic formulas. They are similar to the atomic formulas in the first row, except that now we have used a one-place predicate and applied it to a variable and not to a name. Furthermore, formulas such as H, AB, or G, ABC, they are also atomic formulas. So here I've taken first a two-place predicate and applied it to two terms, and then secondly a three-place predicate and applied it to three terms. And the result of this is an atomic formula. I can also do this using variables. So f, x1, x2 is an atomic formula. Here I've taken the two-place predicate f and applied it to two variables, x1 and x2, or h, xy is an atomic formula, or g, xyz is an atomic formula, and so on and so forth. Similarly, fax would also be an atomic formula. So I can apply a two-place predicate to a name and a variable, and the result is an atomic formula. Now, as you may have expected, we can use atomic formulas to construct more complex formulas. And here you see the inductive definition of a formula that tells you how you can construct complex formulas using atomic formulas. In line 1, we have our base case. Every atomic formula is a formula. And then lines 2 to 6 explain how you can use Boolean connectives to construct complex formulas out of atomic ones. So if A is a formula, then not A is a formula. If A and B both are formulas, then A and B is a formula. If A and B are formulas, then A or B is a formula. And if A and B are formulas, then the conditional if A then B is a formula. And if A and B are formulas, then A biconditional B is a formula as well. Now we move on to quantifiers. So if A is a formula and X is a variable, then the result of prefixing A with the universal quantifier and the variable X is a formula. And similarly, if A is a formula and X is a variable, then the result of prefixing A by means of the existential quantifier and a variable X also is a formula. And nothing else is a formula. So sometimes FOL formulas are also called well-formed formulas, meaning FOL formulas are only strings of symbols that are constructed after these rules and therefore are well-formed. Now, we will, in what follows, take it for granted that whenever we speak of formulas, we mean well-formed formulas and therefore drop the words well-formed. But what you should keep in mind is that if we form a sequence of symbols that does not follow these rules here, then what you have is not a formula. It's merely a sequence of symbols. So here you see a couple of examples. On the left-hand side, you see examples of formulas, and on the right-hand side, you see examples of sequences of symbols that are not formulas. So for example, Gx is a formula. More precisely, it's an atomic formula. Similarly, Fb is also an atomic formula. Now, since Gx and Fb are atomic formulas, our inductive definition of a formula tells us that if Gx, then Fb also is a formula. So you can take two atomic formulas and combine them by means of the conditional sign, and the result is a formula. Now, similarly, the disjunction, if Gx, then Fb, or there is an x such that Fb, that is also a formula. Here we have three atomic formulas, no, actually two atomic formulas, Gx and Fb, and then we have used the quantifier and the conditional sign and the disjunction sign to construct a complex formula from these atomic formulas. And then to give you a final example, there is an x such that Fb, and for all y, Fy, that is also a formula. Now what you see on the right-hand side are not formulas. In the first line you see Gf. This is not a formula because the symbol within the brackets here stands for a predicate. But we cannot apply an FOL predicate to another predicate. We can apply FOL predicates only to names. So when I use the FOL predicate G and apply it to another FOL predicate F, the result is not a formula. Similarly, in the second line, BFB, that's not a formula because of the sign B, the name B that appears before the predicate. So atomic formulas are always the result of applying a predicate to a term, and so when you have a term here, the name B, that's not within the scope of any predicate, that is not a formula. You can't have names that just float around by themselves without any predicate. Or if you look at the third line, if Gx, then that is not a formula because this conditional lacks a consequent. So every conditional always needs both an antecedent and a consequent. So if we omit the consequent, the result is not a formula. Or if you look at the fourth line, that's not a formula because there we just have two disjunction signs, one after the other, and that doesn't work. So a conjunction sign always combines with two sentences to form a more complex sentence, and it can't combine with another disjunction sign to form a more complex sentence. And then finally in the fifth line, you see another string of symbols that's not a formula, and here the reason is because the symbol after the universal quantifier here is a name, B, and that's not allowed. So after a quantifier, we always need a variable, x or y. So for all B, that's not grammatical, and so it is not an FOL formula. Often it will be important to know the main logical operator in a formula. And here I'm just going to repeat some things that we have heard before and remind you of how to identify the main logical operator in a formula. In short, the main logical operator in a formula is the operator that was introduced last when that formula was constructed using our recursion rules, meaning using our inductive definition of a formula. So for example, if you look at this formula here, either if gx then fb, or there is an x fb, the main logical operator here is the disjunction sign. And why is that? Well, if you think of this formula as constructed in a stepwise process, the stepwise process would start with two atomic formulas, gx and fb. Then in a second step, we prefix fb with the existential quantifier there is an x, and use the conditional sign to form the conditional if gx then fb. And then in the third step, we take the conditional if gx then fb and the sentence there's an x fb and form the disjunction that you see here on the slide. So if you think of this formula as constructed in a stepwise process that starts from atomic formulas, then the last logical operator that was introduced in this process is the disjunction sign. And that's why the disjunction sign here is the main logical operator. We have also talked of the scope of a logical operator before. The scope of a logical operator in a formula is the subformula for which it is the main logical operator. So, for example, the scope of the conditional in our example here is the formula to the left of the disjunction sign. So the two atomic formulas, gx and fb, on the left-hand side are in the scope of the conditional. And the scope of the existential quantifier is the atomic sentence fb that you see on the right-hand side. And then the scope of the disjunction sign are two sentences, namely the conditional on the left-hand side and the existentially quantified sentence on the right-hand side. Now, for the definition of a FOL sentence, it is very important to always clearly distinguish between bound and free variables. So let's explain what that is. A variable x is bound if and only if it appears in the scope of either the universal or the existential quantifier. Otherwise, the variable is free. So on the left-hand side, you see a couple of examples of free variables, and on the right-hand side, you see a couple of examples of bound variables. Now let's start on the left-hand side with the free variables. If you look at the formula gx, the variable x is free. It's not in the scope of any quantifier, so it is free. In the second line, you see the formula fxb, and as before, the variable x here is free, since it is not bound by any quantifier. Now the third example is a bit more complicated. There we have in the formula, if there is a y such that gx, then fb. Now, the variable x here appears within the scope of the existential quantifier, but you may notice that here the existential quantifier actually binds the variable y and not the variable x. So that means that here the variable x, even though it appears inside the scope of the existential quantifier, is free, because this existential quantifier binds the variable y and not the variable x. So these are three examples of free variables. Next, let's look at the right-hand side. Here we have a couple of examples of bound variables. In the first line, you see the formula, a disjunction in fact, either there is an x such that if gx then fb, or there is an x such that fx. Now we here have two occurrences of the variable x, and both appear within the scope of a quantifier that binds x. And that's why both occurrences of the variable x here are free. If you look at the second row, we have the formula there is an x such that fb, and for all y fy, Here we really only have one variable, namely the variable y, and that variable appears in the scope of the universal quantifier for all, which binds the variable y. And so this occurrence of the variable y is a bound occurrence. The variable is bound in this example. Or to look at our final example, the formula if all y are f, and then some x is f, that again is an example of only bound variables. The variable y on the left-hand side is bound by the universal quantifier, and the variable x on the right-hand side is bound by the existential quantifier. Now, an FOL sentence is any formula of FOL that contains no free variables. And sentences are special because only formula that also are sentences are true or false. Meaning formulas that contain free variables are neither true nor false. If I say fx, that doesn't have a truth value since it is not clear which object I'm talking about. So on the left-hand side here, you see examples of sentences, and on the right-hand side, you see examples of things that are not sentences. Let's start on the left-hand side. There is an x such that ax, that is a sentence. We have one variable x and it is bound by the existential quantifier. fb is a sentence. It's an atomic formula without any variables, so all variables are bound, so this is a sentence. In the third line, we have the sentence, if all x are g, then fb. Again, we have only one variable x, and that's bound by the universal quantifier, so that's a sentence. Then in the fourth line, we have the sentence, either there's an x such that if gx, then fb, or there's an x such that fb. We only really have one occurrence of a variable, that's the variable x on the left-hand side, and that's bound by the existential quantifier, so no free variables, so that's a sentence. And then finally, the sentence, there's an x such that fb, and for all y fy, that is also a sentence since there are no free variables. Now on the right-hand side, you see a couple of examples of things that are not sentences. Gx is a sentence because the variable x is free. BFB is not a sentence because it is not even a formula, as we have seen earlier. Similarly for if gx, then it's not a formula, therefore not a sentence. In the fourth line, you see the string of symbols. There's a y such that if gx, then fb. Now this is a formula, but the variable x is free since the existential quantifier binds the variable y and not the variable x. So this formula contains a free variable and is therefore not a sentence. And then our final example, for all b, g, y, that is not even a formula since, as before, quantifiers bind only variables and do not bind names. Okay, so we have discussed FOL formulas and FOL sentences. Next, we are going to move on to FOL semantics and discuss the concept of an FOL interpretation and what it takes for sentences to be true on an interpretation.